Hello, everyone. We are the Guinea Force. Our team consists of members Project Lead Michael Iwamiya, Sanid Shabar, and Will Valencia. Today, we will be discussing several topics of our wrist exoskeleton that include the motivation and purpose of our project, background and information, house of quality, the decision matrix, kinematic considerations, view of completed mechanism, degrees of freedom, finite element analysis, and bill of materials and cost analysis.
The motivation and main purpose behind our project is to help people who are in need. Individuals who have suffered from a spinal cord injury, neurological conditions, or even stroke can have extreme difficulties in moving their upper extremities. This can affect every aspect of a person's life, which could lead to physical, emotional, and mental distress. Rehabilitative robotic medical devices, also known as medical exoskeleton devices, have been known to provide mobility to an individual's extremities that may not have been possible without mechanistic assistance. In return, robotic mechanisms can provide support and highly benefit a person's life. In an article published by globalnewswire.com, the author highlights how the exoskeleton market is expected to grow from 450 million in 2024 to 1.8 billion in 2033, alluding to the fact that this technology is becoming more and more popular as the years go on. Our ME157 project focuses on a user's radiocarpal joint, the scientific term for the human wrist. While there are many upper limb exoskeletons that cater to the user's upper arm or shoulder, it is crucial that the individual have mobility and range of motion in their wrists to ultimately allow them to perform activities of daily living. In an article published in the IEEE journal, author Evan Peasant explains how hand and wrist therapy devices are often overlooked in rehabilitation robotics, but are required for regaining the ability to perform activities of daily living. During the brainstorming and very initial stages of our project, we found it essential to research medical exoskeleton technologies. This allowed our team to gain knowledge and insight into exoskeleton designs that have either been published in journals or exist as a product within the market. The next steps were to execute a quality function of deployment in which one of the requirements is to construct a house of quality.
Here is our house of quality, which was assembled during the quality function deployment or QFD stage of the mechanical design process. Starting with the who, our target audience is patients who have suffered spinal cord injuries or are experiencing degenerative neurological conditions and have lost partial motor function, as well as medical professionals such as physical rehabilitation therapists. Moving on to the what, our customer needs for the mechanism to be comfortable to wear and adjustable for different users, be rigid and stable, be able to execute precise movements, portable if possible, and feature at least 2 degrees of freedom. To address these customer needs, some design goals we came up with are to feature smooth surfaces on any part that comes in contact with the skin, so no materials that are rough to the touch or have sharp edges. We also want to minimize deflection and weight by using materials that are not overly elastic or dense, and to design our mechanism around abduction, adduction, and flexion extension movements of the wrist. A couple of current exoskeleton technologies on the market are made by OpenWrist and ExoVantage. The OpenWrist exoskeleton excels in achieving the requisite movement, however, it does not look very comfortable to use, and it being big and burly negates any possibility of portability. On the other hand, more cast-like exoskeletons such as the ExoVantage one provide support to the wrist and can be taken on the go, but it does not really do much in the rehabilitation department in regards to helping the user regain some mobility and motor function. Next up, we have our decision matrix. We elected to use Pugh's method to help us select the best concept out of the 4 concepts we generated. These concepts were graded based on 4 criteria: range of motion, compactness, ergonomics, and safety. Range of motion bore the highest weight for us, followed by safety, ergonomics, and compactness. The 4 concepts that we generated were a stationary exoskeleton without any gearing systems, a stationary exoskeleton featuring motors to provide additional assistance with the different motions, a portable exoskeleton using Bowden cables attached to a motor to generate articulation, and finally, a portable exoskeleton with mechanical linkages to allow the wrist to move in the different directions. Besides considering the feasibility of making each design, when looking at the weighted totals, it is clear that the stationary, gear-free exoskeleton design is the best choice by a wide margin. When designing something new from scratch, it is important to define target dimensions based on the item's intended use and purpose. For our wrist exoskeleton, we don't want it to be too big, so a reasonable value for the length and width of the entire mechanism is around 12 inches for both dimensions. A crucial parameter is the distance between the armrest for the user's forearm and the handle that the user will have to grab to be able to use the mechanism. We measured the length of each of our forearms and came to a conclusion that a value of between 6 and 10 inches would be appropriate. The armrest itself needs to be a curve with a radius of at least 3 inches to accommodate different forearm sizes. We also want to keep the overall height to a minimum because we don't want for the user to have to raise their arms so high to be able to use the mechanism. Lastly, for ergonomic reasons, the handle should not feature a rod bigger than 1 or 1.5 inches in diameter. Pictured here on the right are some measurements taken from the mainframe and the assembly in SOLIDWORKS.
Here is an isometric view of our wrist exoskeleton on the SOLIDWORKS program. This wrist exoskeleton is able to accomplish 2 degrees of freedom, flexion and extension, and radial and ulnar deviation. There are several materials used for this mechanism that include alumina, polyethylene terephthalate glycol, also known as PETG, and alloy steel.
The first degree of freedom featured by our mechanism is shown here. The components are the left and right brackets, the front bracket, and 2 flange ball bearings found from McMaster-Carr. To be able to determine the correct bearings to use for our mechanism, we were required to perform a series of calculations. The first step was to calculate the radial force using formula mass times acceleration. Once calculated, we determined the value of approximately 67 newtons. The dynamic load for the ball bearing with a 95% reliability is found to be 5,070 newtons. The static load rating, or the maximum load the bearing can withstand, is 2,240 newtons. The reliability factor associated with 95% reliability and determined using the charts was found to be 0.62. The bearing factor is 3 since it is a ball bearing. And lastly, the rotational speed is 20 RPMs. From here, we can then calculate the bearing life using the general bearing life formula, and that is calculated to be 1.0921 times 10 to the 11 revolutions. The final step is to convert revolutions to a unit of time using the bearing life in hours formula. Divide 1.0921 times 10 to the 11 revolutions by a factor of 60 and then multiply that by rotational speed. The bearing's life in terms of time was calculated to be 90,993,130 hours. Therefore, the ball bearing chosen is more than compatible with our design mechanism. This first degree of freedom allows the user to perform flexion and extension within the wrist. The natural range of motion within the human wrist was determined to be 70 to 90 degrees. The first degree of freedom is also then connected to the second degree of freedom to enable the user to utilize both ranges of motion. The second degree of freedom featured in our mechanism is shown in the figure to the left. The components directly associated with the motion are the handle, the cap for the handle, the front bracket, and 1 ball bearing designed to fit from McMaster-Carr. To determine the correct parameters for the ball bearing, we follow the same procedures outlined in the previous slide. Ultimately, we found a ball bearing that could withstand 654 million hours of usage during load cases with our mechanism. This second degree of freedom allows a user to perform radial and ulnar deviation.
Here is the finite element analysis that we conducted on our mechanism. We located the 67 Newton force directly on the eye hook in the direction of the negative y-axis, and we fixed the bottom surface of the mainframe. The maximum and minimum von Mises stresses came out to 14.5 MPa and 2.893 times 10 to the negative 7 MPa, which was located near the handle on the front bracket. The maximum and minimum resultant displacement came out to 0.02196 millimeters and 1 times 10 to the negative 30 millimeters, which was located near the handle on the front tip of the front bracket. The maximum and minimum strain came out to be 4.463 times 10 to the negative 5 and 1.639 times 10 to the negative 12, which was located directly on the eye hook. The total amount of parts used in this mechanism is 19 components with a total cost of $874.24. The cost of our mechanism is extremely affordable considering that the wrist exoskeletons in the current market can be upwards of $50,000. Here are all the references that we used for our presentation. Thank you for watching, and Professor Jojo, we hope that you had a wonderful first semester teaching here at SJSU.